Hi, hello. Hope everyone is well. Okay, so the next material that we're going to talk about is 3.26 through 3.31, and I'm going to ask you for homework to do 3.28 and 3.31c. So let's start in here. So let's see. The question here is about inverse, about function inverse, and of course, a person who's taken calculus or linear algebra or whatever class has some experience with function inverses, and we have a sort of an ambiguity. There are two different meanings of function inverse that we have to worry about here. The first is that we sometimes write f inverse of c for the set of things that map to c. So that's a set of things that map to c. So for example, if you looked at the usual f of x equals x squared calculus 1 function, and you said something like f inverse of 9, you would be talking about the set consisting of two things, plus 3 and minus 3. And that's a perfectly standard notation. Everybody in the world uses it. That's absolutely fine. Haven't led you astray. However, it conflicts with the definition of inverse function, is that if g of x equals 2x, then g inverse of 8 could, in theory, mean two different things. G inverse of 8 could mean the set, which happens to have one element, namely the real number 4, or it could mean, G inverse of 8 could mean the number 4, not the set containing a 4, the number 4. Remember when we made a big deal about the difference between a number and a set containing a number? That's for exactly this moment. However, it's not really that important a matter in everyday practice. So we usually don't try to tear our hair out too much about G inverse, F inverse, this kind of notation. In practice, usually the distinction is pretty clear, which it is we're talking about. If we're talking about a one-to-one function, we're usually talking about the single element. If we're talking about a many-to-one function, we're usually talking about the set. Okay, so in practice, it doesn't give us much trouble, but a person needs to be warned that there are two different meanings for the symbol function with a superscript minus 1, and sometimes we mean one and sometimes we mean the other. I'm sorry, I wish there was only one name, but there aren't. There's two names. I'm not doing you any favors if I don't tell you about what you run across. Okay, so if a function has an inverse, then the distinction between the two definitions is minor. If a function has no inverse, then you must mean this one. F of x equals x squared, from the reals to the reals, f of x equals x squared has no inverse because it isn't one-to-one. If a function has no inverse, then this must be what you mean by f inverse of 9 that I talked about earlier. All right, so in particular, the use of the symbol f superscript minus 1 doesn't necessarily imply that there is an inverse function. So it's a little tricky. Okay, so want to talk about 3.26 A, B, C, and D. And it says, the first one says a function has an inverse, so there is an inverse function if and only if that function is a correspondence. So this is an if and only if statement, so the most usual way to prove an if and only if statement is to have two halves, if and an only if. So you might start off, for example, showing that if a function is a correspondence, then it has an inverse. And now, new paragraph, if a function has an inverse, then that function is a correspondence. Okay, it so happens that we are going to, here, let me pop this up. It so happens that we are going to do, come on, there we go. It so happens that we're going to show that if a function has an inverse, then it's a correspondence. And then we're going to show that if a function is a correspondence, then it has an inverse. It just so happens that that's the way I'm doing it. Anyway, so it just so happens that that's the way I'm doing it. So just to go through it here, in the structure of the if a function has an inverse, then it is a correspondence. You expect, when you're showing something's a correspondence, to show that it's one-to-one and it's onto. So you'll see that there's a paragraph here showing that f is one-to-one, and a paragraph here showing that f is onto. So the part that shows if a function has an inverse, then it must be a correspondence, has a one-to-one part and an onto part. So even if you say to yourself, I don't really see how to do the onto part, fair enough, but at least a person can say, well, I got that I need to do this, and I got that I need to do this, and I was able to do one of the two halves, but not the other two halves. Fine. So understanding the structure of an argument gets you at least some way into the argument. Okay, so very briefly here, because it actually, when you boil down the separate parts, it turns out that each individual subpart is not too hard. So we're going to assume that a function f has an inverse f inverse, that's a function that's well defined, that for every element of little c, there's one and only one associated element little d. We got to show that f is a correspondence, so I'm going to do 1-to-1, and in a second I'm going to do onto. For 1-to-1, we have, it's not really a formula, it's kind of a scheme, So to verify that f is 1-to-1, we're going to suppose that f of d naught equals f of d1. Right? I called f of d naught and f of d1 c just to give it a name. And I want to show that d naught equals d1. So that's how you show something is 1-to-1 most of the time. You suppose that f of d naught equals f of d1, and you get down to showing that d naught equals d1. Okay, so I assume that the function has an inverse. So if f of d naught equals f of d1, and I named that thing c just to give it a name, I want to consider the inverse function applied to c. The definition of inverse is that f inverse composed with f gives the identity map. So f inverse of c has to give d naught, and also f inverse of c has to give d1. That's the definition of inverse. And of course, f inverse of c, the definition of function is that when you apply it to an element, in this case c, it always has to give the same output. So d naught and d1 has to be equal, so f is 1-to-1. Okay. And next, we're doing onto next. So we suppose that that f is not onto. So we suppose that there's a c with no associated input d. So there's an output c but no associated input d. There's a c in the codomain, but no associated d in the domain. But then f composed with f inverse can't give this equation, which of course it has to give, because c is not in the range of f. So c is not one of the possible outcomes of f, because we suppose that there's a c with no associated d, so there's no way to get an output of little c, so you can't have the inverse equation. You'd have to have the inverse equation for the inverse to exist. Okay, so again, we assume that the function has an inverse, and we want to show it must be a correspondence. So we show the function has to be 1-to-1, and we also show that the function has to be onto. That's the first half of the question. Second half of the question, you want to show that if a function is a correspondence, then it has an inverse. The simplest way to show that something exists, the inverse function, the simplest way to show that something exists is to name it. That's not always how you show something exists, but typically you name it. You actually produce it, you exhibit it. So I'm going to define an association that takes me in the other direction. That is, I'm going to define the inverse function. The hard part will be showing that it's a function. Showing that for each element of each element of, sorry, I have this backwards. G is supposed to map C to D. I apologize. That's supposed to be capital C and capital D. I apologize. That's a typo. So the obvious thing to do is for each little c and capital C, you let G of little c, the inverse, is supposed to be the element of little d that f maps to little c. There has to be such an element because f is onto, and there can't be two such elements because f is 1-to-1. So what does G output when you give it a little c is well defined. There's one and only one such thing, and so that G is obviously the inverse function. So we're done. Okay, so we wanted to show that a function has an inverse if and only if that function is a correspondence, and we showed it in two halves. We showed if the function has an inverse, then it is a correspondence. We also showed that if the function is a correspondence, then it has an inverse. Okay, second B, if a function has an inverse, then the inverse is unique. Proves to be, you can at least see it's at least a little physically shorter. So if a function has an inverse, then the inverse is unique. So we're going to suppose that it has two inverses, and we'll show that the two are actually equal. The way you show two functions are equal is to show that they give the same output for the same input. So you let C be an element of the domain. The prior item shows that the function has to be a correspondence, so in particular it's onto. So there is there's a little d where f of little d equals c, and f is 1-to-1, so there's only one such d. So that d has to be the output for G naught when you give it an input of C. Okay, so there can only be one precisely because F is 1 to 1. So you get uniqueness. Okay. So C, the inverse of a correspondence is a correspondence. These are sort of getting a little smoother as you go from top to the bottom. The inverse of a correspondence is a correspondence is suppose you have a function and it has an inverse. Well, the inverse itself has an inverse, namely the original function. The inverse of F inverse is F. We've already shown that a function with an inverse must be a correspondence, so that means that it has that is a correspondence. Okay, so a little smoother from top to bottom, and then the last one, if the last one, oops, I'm losing the. No, I lost it. There we go. Last one, if F and G are each invertible, then so is their composition, and in particular, there's a formula for the inverse. So here we go, and again, you can see that it's down near the bottom, so it's relatively straightforward. It's not too long. So here's a verification that that the formula is right. So you take F inverse composed G inverse composed with G composed F. G composed F means G of F of X. F inverse composed G inverse applied to whatever this thing is. It happens to be G of F, but it could be anything. F inverse composed G inverse applied to G. It gives you F inverse G F. The G and the G inverse cancel each other. The F and the F inverse cancel each other, and you're looking at X. Okay, so once you have the formula verifying that sorry, I got to pop it down. There we go. Once you have a formula verifying that it provides the necessary inverse, it's very straightforward. Okay, a couple more here. So in the next section, we're introducing a generalization of functions, a relation. So a function is a set of ordered pairs subject to some restriction, namely the restriction of well-definedness, that if you tell me the input, there's exactly one output, one and only one output. So a function is a special kind of set of ordered pairs, and functions are very, very useful. That's why we did them first. But sometimes it's useful to have a generalization of functions in which you don't have any restriction at all. So a relation is just simply a set of ordered pairs, or ordered triples, or ordered four tuples, or ordered, in general, ordered n tuples. There we go. R is a subset of A naught cross all the way up to AN minus 1. So R is a set of ordered n tuples. It's common for all the sets to be the same, and then we would say that R is a relation on A. If n is 2, you call it a binary relation. Now, binary relations are very common. So in this case, when you have the ordered pair A naught A1, in the relation, we say that A naught is R related to A1. Sometimes you write A naught capital R A1. For other n's, n equals 3, n equals 4, n equals 5, you might say that R is n-ary, like 3-ary or 4-ary, and you call n the arity, A-R-I-T-Y, arity of the relation. Okay, and I just want to do a couple practices with these. So, exercise 3.28 asks a person to list 5 elements of each relation. So let me see if I can manipulate the thing. Correctly. There we go. Okay, so I'm asked to list 5 elements of each relation, and the first is that x and y have the same parity. So, this is 3.28 Roman 1, 3.28 1. I'm looking for pairs x and y where x and y have the same parity. You'll remember that parity means evenness or oddness. So either both x and y are even or both x and y are odd. They're both even. They're both odd. They're both even. And they're both odd. The next one is the less than relation. So the numbers are in a pair if the first one is less than the second. It's just the same as the other one. No, nothing wrong with that. 5 is less than 6. 100 is less than 105. 9 is less than 39. And 0 is less than 100. Okay. If you think about it for a second, there is no function for less than. Less than's not a function, but less than does give you a relationship between two numbers. That's why it's called a relation. Roman 3 is you're looking for triples where x squared plus y squared equals z squared. I don't know if I can remember 5. We'll see. How about 3, 4, 5? How about, does it go 7, 12, 13? I hope so. I don't know. What's the one with 5? Is it, maybe it's 5, 12, 13, and 7, 24, 25. Let's see. 5 squared plus 12 squared equals, yeah, sure enough, it was 5, 12, 13. Sorry about that. 7, 24, 25. And I'm running, quickly running out of steam. So how about if I say, 300, 400, 500, and 0, 1, 1. Okay. And then the last one, Roman 4, is the set of all x, y's in A cross the power set of A, where A is 0, 1, 2. So Roman 4. So I'm looking for x to be an element of A, and y to be an element of the power set of A, where x is an element of y. So how about 0 is an element of 0, 1. 1 is an element of 0, 1. 2 is an element of 0, 1, 2. 0 is an element of singleton 0. And one more, 1 is an element of singleton 1. Okay, so the element, the element construct is a relation. Okay, let's pop that fella back up again. There we go. Okay, so that's a relation. A relation is a generalization of a function in that you have these pairs, for example, if it's a binary relation, but you're not restricted for any to any particular kind of, it's got to be the case that there's always an output. That's not necessarily true. Okay, and then it says verify that for the next one, 29. Verify that for any function, the set Rf of x, y's in d squared, where f of x equals f of y, is a binary relation. So the set of x, y's that map to the same output is a binary relation. And then it says list 6 elements of Rf where f is the real function. So let's try here. Whoops, I forgot to pop it down. Let's try number 29. I'm actually going to try the example first. So it says the example says list 6 elements of R sub f. So I'm going to list. So I'm going to list, I think that the square of 3 and the square of minus 3 are the same. The square of 2 and the square of minus 2 are the same. I think that the square of I can't remember what the square of 1.5 is. 1.5 squared is 2.25. So the square of 1.5 and the square of minus 1.5 are the same because they're both 2.25. The square of minus 2 and 2 are the same. And the square of 1 and 1 are the same. Okay. Now it says verify that for any function f, the set R sub f is a binary relation. So all I got to do is check something very simple. So verify. So let f map d to c be any function at all. It doesn't matter what function it is. Then the set Rf it's the set of x comma y's that are in that are in domain cross domain, where f of x equals f of y, okay, that's clearly a set of ordered pairs. X comma y and d squared. All right, not very well, d squared. So it's a set of ordered pairs, not sometimes a pair and sometimes a triple, ordered pairs, so that makes it a relation. Binary relation. Okay. Okay, good. Only 2 more points, so kind of a fast one today. Wrong one. There we go. 2 more points. So the first point is that if you have a binary relation on a set X, there are four words here, 4 vocabulary words. The binary relation is reflexive if x comma x is an element of the relation. The binary relation is symmetric if x comma y implies that y comma x is in the relation. And finally, it's transitive. If x comma y is in the relation and y comma z is in the relation, implies that x comma z is in the relation. And we've seen some examples of this before. For example, we saw that sometimes 1 comma 1 is in earlier relation, or we might have that 2 comma minus 2 implies that minus 2 comma 2 is in a relation. So those are just words. If a relation satisfies all 3, then the relation is called an equivalence relation. And those are particularly important in mathematics. The goal of this course, in some sense, is to get to equivalence relations. Now, then the last exercise, and again, I'm going to ask you to do here. I'm asking you, in addition to 3.20, I ask you to do 3.31. I'm asking you to do B and 3.32. Okay, so 3.31a that goes into relationship. I'm asked to show it's reflexive, symmetric, and transitive. I might be changing my mind here in the middle about what I'm going to ask you to do. Let me see. Oh, darn these things. Too many windows. Okay, maybe I need a new space. Okay, so I'm asked to show, prove or disprove, that's reflexive, symmetric, and transitive. So I think for this one here, 3.31. A, I think I'm going to ask the 3 questions. Is it reflexive, is it symmetric, and is it transitive? So for reflexive, I'm asked, so to show, to see that the relation G is reflexive, to see that G is reflexive, all you got to do is assume that x is an element of the integers. Then we know x divides x. You know, just from earlier, we saw that in the first couple weeks, even in the case of 0. So x comma x is an element of G. Okay, that's what it takes to be reflexive. B, to be symmetric. Assume that A comma B is an element of G. Is it the case that B comma A is an element of G? And I think the answer is no. I think, for example, 2 comma 4 is an element of G because 2 divides 4, but not the other way around. The relation G is not reflexive. Oh, I'm sorry, forgive me. Symmetric. For example, 2 comma 4 is an element of G, but 4 comma 2 is not an element of G. Okay, so to show that a relation is symmetric, you'd have to show that you have to show the if-then statement. If A comma B is in the relation, then B comma A is also in the relation, and some relations have that property, but this one does not. To show that a relation is not symmetric, you produce. The simplest thing to do is to name a specific thing where you have A comma B is in G, but B comma A is not. The simplest thing. All right, and then C, transitive. And actually, transitive is relatively straightforward because when we first learned this property, we called it transitive. So here, assume that x comma y is in G and that y comma z is in G. Then x divides y and y divides z. By the transitive property, I know it seems sort of silly to name it, so we saw earlier, I'm not going to bother to look back and see what number it is, that x divides z, and so x comma z is in G. Okay, so to show that something is transitive, you assume x comma y and y comma z, and you got to go on and show that x comma z. To show something isn't transitive, you only have to name a specific example of an xy and a yz where it fails to be the case that xz. So for A, to show that something is reflexive, you simply have to show that for all x's, x comma x works. To show that something isn't reflexive, you only have to show one x for which x comma x doesn't work. That's why I worried about 0. For symmetric, to show something is symmetric, you have to show the if-then statement. If x comma y is in G, then y comma x is also in G. To show something isn't symmetric, which of course is what I did here, you just have to show one counterexample. The most straightforward thing to do, in fact the thing you should do, is to name a specific element. 2s and 4s works the best. And likewise for C. To show something is transitive, you assume that x comma y and y comma z are both elements of G, and then you go on to show that therefore x comma z is an element of G. To show something isn't transitive, you have to show that the best thing to do is to name a specific x comma y and y comma z for which there's no x comma z. Okay, so I think I changed my mind. I know I have down here the two numbers that I said earlier, but I think I changed my mind. I think what I'm going to ask you to do for homework is 3.31 B and C. I think that, and I'm going to skip 3.32 for the minute. So I think that's that'll be the homework because these are striking me as good examples. Okay, very good. Okay, so let's see. So I'm going to ask you to do for homework 3.31 B and C that follow the model of A. Okay, great. Okay, hope everybody is well, and we'll see you getting down near the end. It's kind of exciting.